today, the idea is to spend a little bit of time on one pillar of open science, which is really important, which is software, and particularly software source code, how software is developed, how is this used, and what we need to actually handle it properly in a framework of open science. Let me start with a little bit of introduction on my side. So my name is Roberto di Cosmo. I'm a full professor in computer science at one of the many universities in Paris. Now I'm on leave at INRIA to work on software heritage, which is a project we will touch upon later on in the presentation. I spent, as you can see, I'm not yet, no longer so young, so I spent a lot of time doing research and education. I spent over a quarter of a century in everything related to free and open source software. In the last 15 years, I worked in different organizations, institutions to try to build structure at the service of the common interest and common good. So the last one is the Software Heritage Initiative we will discover. I'm also a member of the National Committee for Open Science here in France, and I'm co-chairing a task force in the EOSC, the European Open Science Cloud, dedicated to infrastructure for software, which will just give you a little bit of background. Now, let's start with a little bit of introduction here. If you, in your work, in your daily work, you see you are using software all the time, and even in your personal private life, you cannot do anything reasonable today unless you have access to software. But what is important when we talk about science and research is to remember that actually software doesn't come out of the blue. It is actually written by humans in the form of programs. And actually, as one of my reference professor in computer science when I was a student many years ago, wrote on a beautiful introduction to his book, Structure and Interpretation of Computer Programs. Actually, programs must be written for users, for people to read in the first time, and only incidentally for machine to execute. Well, when he wrote this in the 80s, you could think as, well, it's a typical professor telling the student that if he cannot read anything reasonable out of the homework, you will get a bad grade. But it was much deeper than that. The fact is actually software is a living object. And so you write it, and you know you will have to modify it, to fix it, to adapt it, to use it in different way. So it is very important to use software as a way of sending a message to another person that will need to adapt it or use it or modify it later on. When this was written back in the 80s, there was not much open source software available, so it was kind of difficult to follow the message. Today, some 40 years later, we have access to an incredible amount of source code. And for example, here is a small fragment of a piece of source code that was used to control the landing module of the Apollo 11. Actually, there was 60,000 lines of code written at that time, and I would like to take the occasion to remind that at that moment, the direction of the program for writing the source code of Apollo 11 was led by a woman, Margaret Hamilton, who is an incredible person. She's still alive and still runs a consultancy for quality, highly critical software. But you see, back in the 60s, source code was kind of unreadable, right? Because you had all these mnemonics for assembly code that luckily we don't use anymore. But even then, you see, this part on the left is the assembly code that went to the machine. The part on the right, after this number sign, were comments in plain English that are actually this message sent by the developers to the other person, the engineer, that we need to read it or understand it later on. And well, if it is clear that this part in the source code that will never survive in the binary, it is only in the source code, is important, then you could think that that was important just because the programming language was very low level. Actually, it is not that clear that it is just because the programming language is low level. If you jump ahead a little bit, so this is in the 90s, there is a beautiful piece of source code extracted from the Quake 3 arena, which is a precursor of Call of Duty, etc., this compute is 1 over square root of x using a beautiful trick. I mean, it would take some time to understand, but you see even here, the names of variables, the name of the function, the comments, even some of the comments, well, are not necessarily helpful, are essential to understand what is going on. So it is not just a matter of how high level the programming language is. You really need extra information for the people. To sum it up, as Len Shustek, who was a board director of the Computer History Museum, a beautiful institution in California that retraces the history of computing, access to the source code of software provides us with a view into the mind of the designer. So that's why it is so important to have also the source code, not just the binaries. And when you look in details at source code, you discover that source code is not just data. Sometimes you have a tendency of thinking the software and source code are just data. It's a sequence of bits, right? Some bits are data, and that's it. Well, no, I mean, data is, when you think about data, data is generally something that is used to do some kind of processing after all, okay? So, I mean, meteorological data, biological data, this is something you use as a datum data for doing a computation. But actually, source code is very special, much more than just data. It's a living object that evolves over time. Some projects take decades to be developed, and the development history is essential to understand what is going on. And also, it is extremely complex. It can be complex in two ways. It can be complex because a single project contains millions of lines of code. Think of a Linux kernel running on many machines, or in your phone, Android phones today, it is over 20 million lines of code. And this is a form of complexity. Then there is another form of complexity that comes from the fact that we have a tendency of building by reuse. And this means that even when you, for example, if you launch your Python interpreter and type a simple line like import matplotlib to load a graphics library, behind the scenes, you're actually pulling in tons and tons of other components and dependencies which are needed to actually make your routine work. And this depends on a large web of dependencies on sophisticated developer communities. So it's not just a piece of raw data that you get out of an instrument. It's much more complicated than that. And what we also observe today is actually this precious knowledge is today in danger because many people that actually develop computing are passing away. We are losing their knowledge, but also because we were used to just rely on very popular code hosting platform for doing our collaborative work. So when I started using Forge some 20-something years ago, it was SourceForge that almost disappeared. Then we use Google Code and Gitorious, now GitHub, etc. But you see Google Code closed it down, and Gitorious was acquired and closed it down again. So there is a real danger of losing what we're doing. So this is a general introduction of software and why source code is important, why should we care about it. But if you focus now on open science, you see that actually there are many pillars of open science. Of course, we have learned about open access, the best practices, the open repositories, the question about licensing, a long story. Then you have also explored a way of handling open data, which is also a complex issue on itself. But then we come to the third pillar, which is very important, which is open source repositories. Actually, if you think a bit about it, if you take a paper, read a paper, and the paper say, we have analyzed this bunch of data here, and then we have performed this simulation analysis, etc., and the result is 42. Well, if you really want to understand what is going on, to rebuild the experience, verify it, or study a variant of it, the paper is very important. It describes what is going on, but then you need the data. If the data is missing, basically the result is just an act of faith. And then you also need, even if you have the data, you also need the software. Why? Because sometimes the complexity of the transformation of the evaluation you are doing in the software system is much more than what you can put in the paper itself. Or maybe there may be mistakes or bugs or whatever. So the only way of knowing what is going on is actually to have access to these three pieces of information and use them together. So of course, the links are extremely important. And then if you put your research hat on, day-to-day research hat on, you will discover that you have a bunch of needs when it comes to software. Okay? I write an article, I'm using a piece of software that I developed specifically for this article. I would like to know where to put this piece of software in such a way that it will be available to other readers, including myself, in a week, in a month, in a year, in 10 years. Okay, and also I need to be able to pinpoint exactly the version of the software I'm interested in. I need to have precise references, because software evolves over time, and what worked with version 1 maybe doesn't work on version 2, you know, I mean, you need to pinpoint exactly what you need. But of course, you want to find useful software that you can use in research and produce it by other people. You want to get credit for software that has been developed by you if somebody is reusing it. And in general, you may want to verify or reproduce and produce the result of others. Then when you grow older or higher up in the hierarchy, you will discover that you need also to produce reports and maintain a web page, what is the software to which our lab or university has contributed, etc. And when you go very up in the research organization, of course, you need to have a knowledge of what are your software assets for many reasons. I mean, one can be technology transfer, the other can be just measure the impact that your research organization is having on society in a way or the other. For this, you need to track the software contribution across all the institutions. Now, if you want to do this, you discover that you need to address 4 key needs, okay, that I'm proposing here to look at in order of increasing difficulty. One is archival, and where should I put my software in such a way it doesn't go away. And remember, code hosting platforms are not archives. They can be closed down, or the software can be erased and moved elsewhere. So you need an archive. Then you need a way of referencing the precise version in such a way that you do not depend on again, mechanisms that can go away. Then you need to describe your software in such a way that can be found and reused properly. I mean, this is a little bit more complicated than just having the exact commit hash of what you did. And then getting credit and citation, this is even more complicated, it becomes more political, because then when you have a software where 20 people contributed to, who should be in the author list, who should be in the thank you list, and who should just get the coffee with you because give you a little bit of a hint on a detail of the software. I mean, this is a human operation that requires some time, especially because it is connected then to evaluation. Well, if you want to address all these 4 needs in a proper way, we need infrastructures that are designed actually for software source code and not abuse infrastructure designed for data or for publication that are not designed for software. But the good news is that now we have one, and we will see this in a few minutes. But before going there, I would like to take a moment to let you think. You see, what these needs, archive, reference, describe, insight, are typically for people that has a piece of software that has already been developed, and then you have developed this software, you want to actually make it available to others, make sure it can be referenced properly in the literature, etc. But you have other issues that come before these 4 needs and other issues that go beyond these 4 needs. So let me hint at them. But before this issue, there is also the question of how you develop your software. What are the proper development practices you should put in place to actually make it work before you archive it, okay? So then typically you need to learn how to use a version control system, how to add proper metadata information, which is nothing new under the sun, and this has been developed decades ago, but it is important to know how to do it. Then how to properly set up a build system, how to provide tests, etc., etc. And also how to go towards a community if you want to go in a community direction, so typically documentation, etc. All of this will be touched upon by Liam in the next half of this afternoon, so I will not touch upon this. Then there are other issues that go beyond that. So you have already developed your software, you have already archived the references, etc., but then you discover after a while that there are many other issues coming. I mean, an issue of sustainability. You had a nice experimental project that produces a piece of software that you believe is important. Then the project money runs out. What do you do? I mean, to keep maintaining it over the time. And even when you develop your software, I mean, what kind of license should you use? I mean, what is the best choice? we are in open science, right? So it should be an open source license in some sense, but there are many open source licenses. So which one is best fit to what you want to do? How are you going to fund it over time, etc., etc. So these are global issues that need to be addressed at the research level. And also the issue evaluation. And so we spend part of our time research developing software. We would like to get some credit in exchange. We want the time spent developing precious, valuable, high quality software to be taken into account in our career evaluation. So here we have seen the disaster created by numerical indicators like impact factors, H-index, etc. in the past in other disciplines. So we need to think about ways of evaluating the contribution to software that is not just counting the number of commits you made or the number of comments you made on a line of code. And the other point to take into account is that all this is actually being structured. So slowly, the organization around us are working on something that will become a software management plan, metadata, the identification, regulation, standards, etc. So this will be coming too. But I will not touch upon this part here because we have just a very limited amount of time. If there is interest, maybe in a future event, we could look together at policy, regulation, organization, which is a complex issue because it depends on the country, etc. Anyway, so let me move now to a more practical part of this presentation after a general introduction and a bit of motivation. And I told you, I mean, now for these 4 needs, archival, reference, description, and credit or citation, we need specific infrastructure built for software source code specifically. And well, one of these infrastructure is software heritage. So let me introduce it to you. Software heritage in a nutshell is an initiative that has been launched some 7 years ago, actually officially announced 5 years ago. We just celebrated 5 years at UNESCO in November. It's an initiative that has a precise mission to go out and fetch, collect the source code of all software that is publicly available, make sure it is not lost, so preserve it, and make sure it is easily accessible for everybody. So this mission actually has 3 sides. One is preserving the past, but it is also structuring the present and the future, providing you with a kind of Library of Alexandria of all source code that are written and even written today in such a way that the knowledge is transmitted and not lost. So in one sense, what we are building in software is at the same time a kind of a reference catalog, because all of us, we are using tons of open source software from all over the world. But this open source software is spread in many, many different places. So you have GitHub, which is very popular today. They have millions of projects, etc. But there is a long tail of many, many other platform and distribution systems where you have tons of other software that you cannot find on GitHub. So you need to find a place where to catalog all this. And this is what we are building. Then you need to build an archive. An archive is a place where you put a piece of information, it stays there. Again, a code hosting platform is not such a thing. You can go create a project, then you decide to close it, erase it, move it elsewhere. There is no guarantee that what you find you there today will be there tomorrow. Okay, so this is relevant archive, and this is what you're doing. And finally, but I will not touch upon this today, it is a first building block of a research infrastructure for exploring the galaxy of software development today. How is this built? So we design software as a kind of an infrastructure. So we stick to our mission, so collect, preserve, and share the source code to enable tons of applications in different areas. For example, there are applications in cultural heritage. We were studying how to rebuild the history of landmark legacy software that was important in the evolution of computer science or other disciplines. We are working with industry to provide industry with a reference knowledge base about all the software developed worldwide. We are focusing on providing services to academia. I mean, the presentation I give to you today is part of that mission to provide a place where to actually store all the research software used in research application. We are working with public administration that need a place to actually store software built on public money for transparency, accountability. But we don't do any of these things, okay? We just provide the infrastructure layer there, which is already quite complicated. I mean, if you look at the website, we can have a look later on. We have already indexed over 175 million projects, and this is over 12 billion unique source code files. So, so the important point here is that software is not just an archive for research software, it is an archive for all of software. And the reason is, when you run a piece of research software, you may depend on a library that is not developed by research, that comes from elsewhere, or an operating system, or a compiler, etc. And you need all of this if you are looking towards reproducibility. So we are kind of everything, not just what is needed by one or the other of the stakeholders. Now, how this global initiative can help in addressing these 4 needs for research source code. Well, first of all, we are providing this archive. Okay, and sorry, the slide it is 10 billion, 150 million. You have seen it has already grown since this slide was written. What we do is actually go out and we connect with all the platforms that software is developed or distributed. We build connector to it to get the list of all these objects. In some sense, so this is a catalog. And then we fetch the source code with all its history from all of these places. And when we fetch it, we actually discover that it is maintained using different technology. It can be Git, Mercurial, Bazaar as version control system, can be Python packages, JavaScript packages, cargo packages, forgot whatever. So an incredible Babel tower of formats and standards. And so we go the extra mile and we actually convert all these formats, all these versions into a single gigantic graph that contains the history of development of software worldwide. But technically, this is a Merkle graph we built out of cryptographic signature, but this is nothing that we invented. It is the standard way of doing software development today. Think of it as a kind of a Git at the scale of the planet. So in some sense, the good news is that sometimes some of your code, some of the research code you are relying upon, maybe is already archived in there, right? So because we actually proactively go and crawl things. But we also added 2 new functionalities. One which is called Save Code Now. You find it by going on save.software.org. There you can point our crawlers to a particular repository, a particular archive which is important, a file which is important, in such a way that it is archived in a couple of minutes automatically when you need it. Or if you need to refresh a repository that is important for you because okay, you have a submission at midnight, you just, again, click on this button, it is updated. And we also opened up a path that is called Deposit to reference platforms or open access portals like the National Access Portal in France, which is HAL, but we are working also with the Node or with others to make sure that if people want to deposit software with curated metadata there, we collect it with the proper metadata. So you see, the archival part is kind of well covered by this infrastructure, which is designed for software. And there you will find all kinds of software, not just the one built in your lab. And the other point is that due to the particular structure, data structure we use, this gigantic Merkle graph, to store everything, again, like imagine Git, we are also providing to each of these software artifacts a specific identifier, which is actually intrinsic in the sense that it is computed from the object itself. Basically, it is a cryptographic hash. No? It can compute from the software itself. Then the question is, how do you compute the hash of a full project, not just of a file, when this is a traditional Merkle construction? So these identifiers, I will not have time to go through them in details today, have very important properties. I mean, they do not depend on a registry. Okay, you can compute the identifier for your own piece of software by yourself if you want. and somebody else can do it on another side of the planet, you will find the same identifier. You will know you are using the same thing. So you see how important this is for reproducibility, right? Then, since it's a cryptographic identifier, it also gives you integrity, the ability, looking at the identifier, you download something that corresponds to it, you recompute locally the signature. If it matches, then you got the right thing. Otherwise, somebody tampered with it, which is not a good thing. Well, this is basically a standard which is now included in the industry standard, like the Software Package Data Exchange of the Linux Foundation. You have equivalent in Wikidata that points to this, and it is slowly getting adoption also in academic areas. You also have for the description. This is not our core business, because the core business of software is archival and reference, right? But we are also trying to help in describing side. For describe, we actually contributed the code meta generator, which is a tool that allows you to produce normalized metadata about a piece of software you write. And for citation and credit, we released finally support for having software properly handled in BibTeX, which is used in the TeX LaTeX processing system, which is very popular in many fields of research. So this is available on Citan, actually the latest version in 1.2.3 and not 1.2.2, but doesn't matter. And you can also already use it in your publications. So this is a model where I should try to give you a little example of how actually this all works. So let me take a couple of minutes about this. So what you see here, this is actually the Software Age archive as it is today. So if you look at it, here you see all the places where from which we regularly collect projects. So you see Bitbucket, GitHub, GitLab, Debian, Segit, NPM, PyPy, etc., etc. You see also the forges where important pieces of software were present, but they were closed down. So GitHub in 2015 closed it down with 122,000 projects in danger. Now they are saved. Google Code closed down more or less the same moment, almost 1 million projects now already saved. And last summer, in Bitbucket also closed it down, part of its support. So not all Bitbucket, they are alive and kicking, but Mercurial disappeared, and this meant over 300,000 projects in danger that were actually saved in the system. Now we have also journals using it regularly. And if you want to see how this actually works, let me give you a simple example. For example, this is, if you look for a particular project in the search engine there, that looks for the moment only in the URL of the project, not inside the code. This is one project of mine. Okay, it's a small library to do a MapReduce implementation of multi-core. You see the presentation of the archive is really designed for source code. You can actually navigate inside the source code, actually look at the content of the files, and you see for every content of the file, you have the highlighting in the typical kind of programming language that is used. And then when you navigate in your file, you can at any moment select a fragment of code that is interesting for you. So I click it on this line 7. Now I will shift click on line 80, just to give an example. And all the time you notice that we had this red tag here. Well, this is a permalinks tag that allows me to get an identifier. This identifier for the file, okay, the hash of the file plus the prefix. I can also add some contextual information that says this file is found on this particular origin, inside this particular revision, that has this name in this particular path. And what I'm interested in are these lines. So if I copy this identifier and I put it in a paper, in documentation, in a tweet, in a web page, and then somebody clicks on it later on, you see what happens. And now I'm circulating the click by copy pasting. What happens, you will be put in front of the same part of the archive on the same file, in the same fragment, and in the same context. That is, if you go up here, all this contextual information, I mean, the comment, the revision, hash, branches, the source code, the origin, etc., is all the same as the one that I wanted to reference when I wrote my publication. I mean, this is something I really wanted for a very, very long time, and finally I can do this in my paper. But this kind of thing is available at all levels, so you can get an identifier for a directory, or for a revision, or for a snapshot, not only for a source file or a snippet of code. You see, so that's particularly useful and interesting. And imagine that you see that this last visit, which was March 21st, is not up to date enough. In this case, it is up to date. You can always click on Save Again, for example, and you are just telling our archive, I would like to have a fresh update of the version that is archived. And when you do that, you will see that this is put here in the list of requests for Save Code Now requests. And you see there are also already over 100,000 requests that has been done manually or mechanically for having this kind of updates. A request can take a couple of minutes to archive, but if you want to archive the full Linux kernel, can take a couple of hours, okay? But typical things are very fast. And when you do this, you can also add inside your code, if you want, some metadata information that can be described in a particular format. For example, this is called meta.json. They describe the authors, their affiliation, etc. All the information that is important for creating a report automatically later on, you see. And you do not need to write this by hand. There is a tool that allows you to prepare a validated JSON file as you want. And you can also add, if you want, a sample bibliography entry for describing your software. Okay, and so this is actually based on bibliotheque software that can be reused regularly. Well, okay, so it was just a very short demo to give you an idea of what can be done. In the slides that you will have here, all the blue links actually are links to part of our demos on related information on what you can do with this archive. So do not hesitate in clicking into them. I just do not have time to go through this right now, and I think I have just a couple of minutes left. So let me move on now. You have seen the general organization of this infrastructure. It is free of you for use. It is fully open source. Everything is available. And you know, it is already useful today because look at what happened, for example, when we saved the 250,000 project endangered on Bitbucket a little time ago. So in summer 2019, Bitbucket, which is a very popular platform also, announced that they will phase out support for this version control system, which is called Mercurial. Oh, all of a sudden we discovered we had to move into firefighter mode and go and try to save this 250,000 project before it went away. So we got some funding from a foundation in the Netherlands and contacted a company which is specialized in Mercurial. We worked together with them so in basically 6-8 months, we developed the technology and we imported everything. So when Bitbucket pulled the plug in July 2020, just a couple of days later, the full version archive was live on Software Heritage and is now being ingested. Well, why I'm showing you this? Because what happened is that just a few weeks after, a colleague of yours in astrophysics somewhere was alerted that the software associated to one of his earlier publications disappeared, because here's the publication, he had a pointer to the code hosting platform Bitbucket, not to an archived version. And he was pretty upset because he thought that everything was lost, but then he discovered that a full copy with all the history of development, I forgot to show you the history of development, was completely archived in Software Heritage. So the bottom line here is that even if Safe Code Now is very important, depositing is very important, etc. Sometimes you forget, sometimes there are something you don't think about. So it is very important nonetheless that we have this systematic approach of trying to go out and archive whatever we can find, because in these cases, we can save the day for colleagues, like in this case. Now, let me finish. As a road ahead, just if you are curious about software heritage, this is a really initiative designed for the long term. So we have an agreement with UNESCO. We have many learner society and organizations that support our vision. And we are building an economic model based on a large set of partners. So you have INRIA here, who was a founding member. So you put most of the resources at the beginning, but many other organizations supporting our work, and particularly Sorbonne University, which is one of the organizers of this presentation, is one of the key academic partners. But you have really academia, public administration, private companies, all kinds of partners around the table. And there is growing adoption in academia. So the National Portal for Open Access in France is using software systematically for software. In mathematics, you have a reference catalog for mathematical software, which is called SWMath. It links to software for the archival. You have many journals in different areas that are starting to use software for the reference archive and the identifiers. And from the policy level, so you have a national plan for open science that was published last summer here in France. The focus is on many things around software, and in particular recommends and supports software for archival. And the same is done at the European level in this IOSC report. And again, there are very simple, very easy guidelines for archiving and referencing your source code. It is just a couple of lines that you can follow. There is also a paper here, ICMS, that shows you how to do the things. Maybe just a second, because this is important. Let me see if I can show you this. If you go to the main software heritage page here on archive, you see there are many things, but for example, on Save Research Software, there are these guidelines, which is just a very simple web page with the key things you need to do, which is extremely simple. And then how to use the software. You have a live demo, how to get your identifiers and how to use them in, for example, in a BibTeX reference. Here you have a short tutorial about this. So again, we really tried to make as much as possible available for your use. Let me see. No. Okay. And now moving to the conclusion, if I can manage to convince this thing, okay, to work, fine. Now up to you. So I try to give you quite a broad overview of different things you can do with this particular platform. You can use it right now to archive your software references with the proper identifier. You can use this bibliographic style in your journals or conference proceedings, etc. And there are many other things you could do. I mean, you can contribute to the source code. Everything is open source. Some of you might be interested in working with us. There are positions open. Just go to the website and look at it. And generally, telling people more about the existence of this infrastructure is important, because even if it is a relevant infrastructure, it is young. And, you know, it takes time for people to be noticed. And your help will be important. So I think I will stop here, and now we can take any question that can be around the table. Let's see. I do not know, Cecile, if you want to animate the session, the question session.
Well, we can take the question at the end of the session if you prefer. I don't know, perhaps there will be more questions, but I don't see question for now in the chat. But
okay, so maybe we can move to the presentation by Liam and then the question at the end. So Liam, I will make you, how can I give you, wait a second. I need, is there. So if I do. Okay, so now you should be able to share your slides. Fantastic.
Thank you very much, Roberto. And so I'm going to discuss a little bit the topic of how you go from kind of writing some software to writing reliable and maintainable software, and some best practices to accomplish this goal. So very briefly who I am, I'm a research software engineer at Heidelberg University. Currently, there are 3 of us in the Scientific Software Center, and we offer researchers at Heidelberg University help with their software development on both kind of very small scale and larger scales. We offer consultation, advice, and teaching and training. If you're interested in learning more, we have our website here and our GitHub page. And in particular, on our GitHub page, we offer some coding guidelines and some template repositories to help you get started with new projects. And so research software is increasingly vital as a part of scientific research. And importantly, I would say it's not just kind of code written by real programmers. Anything that is software that is involved in producing some research output is research software. So that includes any simple little Python scripts that analyze data. These things are also software and should be treated as software. And as Roberto said, this is an intrinsic part of reproducible science. So for people to trust your research, they need to trust your software. And at least in my opinion, this means that software should be open, should be reliable, and it should be maintainable. And so I'm just going to go through some kind of basic best practices for producing reliable, maintainable software, which are so open source development, so making your code public, version control, so using a tool to follow the history of your changes to the code, testing, so writing code that tests the code, documentation, so writing down how to use the code, what it does, and then 2 more which are maybe somewhat less obvious. So one is continuous integration, which is just having a server or a system which automatically does things as you make changes to the code. So it could be running the test suite, it could be formatting your code. And community involvement is a very broad topic, but at the very simplest level, it's just providing a way for people to be in contact with you to report bugs or suggest new features. So I'll go through each of these with some more details and then show a quick example for each case. So open source development is very simply just making your source code publicly available. So nowadays that often means GitHub. It's probably the most popular place for doing this. There are various other hosting providers. There are also services like Zenodo and Software Heritage, which do more than just kind of host your source code, but also preserve it for a long time, provide you with a URL and a citation and things like this. So what are the advantages of making your source code open source? So firstly and primarily, it makes it easier or possible for people to reproduce your results. So from a scientific research point of view, that's really vital. It also means people can find mistakes and bugs. And if you're really lucky, they'll tell you about this. And if you're even luckier, they might even provide or offer a fix for any mistakes or bugs that they find. It also allows people to offer suggestions, make improvements. It makes it easier for other people to cite your work, and it makes it easier for other people to use your work and maybe extend on your work. And so overall, if you make your source code open source, you're giving other people confidence in the value of your code. It's a statement you're making saying this is worth sharing with the world. I'm proud of this. And so here is an example. So this is a library called PyBind 11, and it's just a a kind of randomly picked project, which I feel does a good job of all of these different best practices. And so this is just the GitHub main page of this project. So version control. So what is version control? It's just using a tool to track changes to your software. So again, mostly nowadays, this means Git, Subversion and Mercurial, 2 examples of other alternatives that are still being used. And so why would you do this? So the key advantage is it makes it very easy to keep track of changes to the code. So what has changed, who changed it, when that change occurred, and why it happened. It also makes it very easy to refer to a specific commit, tag, or version for reproducibility. So it's more than just, here is my code and it's open and you can use it to reproduce my results. It's, here is the tag or the commit hash showing exactly which version of all the bits of code in here I used for these results, and you can then reproduce them yourselves. By the same token, it's easy to undo or revert changes. And as projects grow, it's also vital, basically, to be able to allow lots of different people to collaborate on the same code effectively. And this gives other people confidence in the history of your code. So making your code open source gives them confidence that you think it has value. And here you're making the entire history open as well. So it's very transparent. It shows how the code was developed, the history, and it gives people confidence in your code. So an example from the same PyBind 11 library. Here we see a commit, which was written by some author, and we see the date it was made. We see the change to the code that it involved. And you can also see, not shown here, a commit message where they explain what they're doing and why. So testing your code. So testing is writing checks that the software is working correctly. And what are the advantages of doing this? Well, the first one is that you ensure your code as you write it is correct. But once you've written the test, it continues to have value going forwards in time. So it maintains this correctness of your code. If your function was correct, but then it depends on something else that changed and it breaks, if you have a test, then you'll realize this and you can fix it. And more generally, if you have a test suite, you typically find bugs earlier and more easily than otherwise. So for example, without a test, something changes in your code, you continue using it, you generate data, you make your publication. If at this point you find out there's a mistake, 1, it's a big disaster, and 2, it's very difficult to find out where the mistake is. You have to go back through all the changes that happened in your code, try and work out the source of this problem. If you have, on the other hand, a test suite, then the very second that you make this change that makes the problem, hopefully you have a test that fails, and then you can instantly see where it's gone wrong and you fix it before any kind of downstream problems have occurred. In terms of keeping your code maintainable, having a test suite allows you to make changes or refactor your code, so rewriting it to make it clearer or faster or whatever it is, without being worried about accidentally breaking things. If you try and refactor code where you don't have any tests, it's a bit like driving a car with your eyes closed. You don't really know at what point disaster is going to strike. And if you have a good test suite, then it really helps you with maintaining your code, because you can just make changes and you have a kind of a seatbelt in the form of your test suite to prevent you from making too many mistakes. It also helps other people contribute effectively to your code, because they can also then try and make a contribution, and the test suite ensures they're not breaking a whole bunch of things without understanding what they did wrong. And it can also act as a kind of complementary source of documentation, serving as examples of how to use the code. And so having a test suite gives others confidence in the correctness of your code. It shows that your code is correct. It shows that that is important to you, the author of the code. And there are a bunch of different kinds of tests, so I'll just describe briefly some of the most common ones. So the first is unit tests. And this tests a small isolated piece of functionality, say for example a little standalone function. And a typical test suite, you would have a majority of unit tests. There's a lot of these, they're very simple, they test simple things, and when it fails, then it tells you exactly which bit is not working properly. Then you have integration or system tests, where you test larger interconnected pieces of code. And then there are some more interesting ones. So smoke tests, which is just a kind of a sanity check. You run it, you check that nothing disastrous happened. And this has two interesting sources of the terminology. So one is from electronics, where you would just switch on your machine and see that no smoke comes out of it. And an earlier origin for the phrase is actually from plumbing. So if you build a set of pipes for water in your house, before you put water in it and see if it leaks, you can fill it with smoke, and it's a kind of a less destructive test. And then there are two other types of tests I would like to mention. One is regression tests. So here, if you find a bug or a mistake in your program, then you ideally would then write a test which demonstrates this bug, and then you fix the program, and then your test passes, and you're done. And this regression test you keep, and it checks that your mistake doesn't come back. And then finally, approval testing is a slightly kind of different approach, where if you end up having to work on a legacy code base, so some old piece of code, maybe very large, maybe complicated, which doesn't have tests, so it would be impractical to try and retrofit the whole set of unit tests, integration tests, all of these things. Instead, you can just have some input, you generate the input, you run it through the software, you record the output, and then you make a test asserting that this is what the software does. And it's just a kind of a very quick and cheap way to get some tests for a system before you start making changes. And so here's an example from the same library as before, and we see here it has a bunch of different tests, so testing each different piece of functionality. So documentation. So this is just writing down how your code works, how to use the code. What are the advantages of doing this? Well, it helps users understand how to use your code. It helps developers, which may include yourself in the future, understand how to modify the code. It also encourages people to learn about your code. It's kind of a bit of positive advertising for your code. The fact that there is documentation is a good sign, and it's typically easier to read than trying to read the source code directly. And so overall, having documentation gives other people confidence in the usability of your code. So what is documentation? What kinds are there? The kind of level 0 of documentation is the source code itself. And as Roberto said, the point of the source code or the target audience should be other humans. So the first kind of documentation is source code that is written with the intent to be clear and understandable by other people. In practice, that's not enough. And so there have been multiple kind of layers of documentation on top of this. The first one will be just adding comments to the source code, so for you and other developers to read. Then there might be API documentation, so application programming interface, describing how your function or library can interact with other pieces of software. So this is typically aimed at software, so aimed at developers or power users. Then there's kind of traditional user documentation, where you write documentation for your users. And for both of the user documentation and the API documentation, I find that including examples is really very helpful. And so here, once again, the same library, we see about documentation is a web page with initially some basic instructions, how to get started, and then advanced topics, and a bunch of reference information. And this documentation, incidentally, is part of the GitHub repository and is built along with the software itself. And that helps you keep the documentation and the software in sync. So continuous integration. So this is just any kind of automatic check that occurs in between you making a change to your code and that change being accepted and merged into your code base. And so what are the advantages of doing this? So one advantage is you can ensure that all your tests pass before you merge the change you're intending to make to the code. If you're working with multiple people, then it can be very helpful to have automatically formatting applied to the code so that everybody's writing in the same style, minimizes the difference between diffs of different versions. You can add requirements such as new code needs to be covered by tests, and these requirements can then be enforced by your continuous integration. It also allows you to test the code on multiple different platforms. So for example, running your test suite or compiling your software on Windows, on Mac, on Linux, or using different versions of Python or whatever the dependencies are of the code you're working on. You can also use this to automatically deploy new releases of your software. And overall, having automatic checks like this helps people improve the quality of their proposed changes to your code. And so here we see what that looks like for this library. So this is using the Github Actions infrastructure. And on the left, we see a whole bunch of different jobs. So each one of these is a separate job which ran on a computer somewhere with a different version of Python, maybe a different operating system. And we see that it sets up a system, it compiles all the code, it runs all the tests. And this then has to pass before any proposed changes are integrated into the code base. So community involvement, this is enabling people to contribute bug reports, feature requests, maybe even code. And the advantages here, so a lot of them come back to the same advantages of making your code open source in the first place. So it allows people to find mistakes and bugs, hopefully even fix these mistakes and bugs for you. People can also improve the documentation, offer suggestions for changes, improvements. People can also help each other to use your code. And as you get more contributors, both to code and to documentation and users, this helps to make the project more sustainable. And so building a community is kind of, I would say, the key to long-term success of a project. And yes, this advantage is that it helps others both to use and to contribute to your work. And so the example from our library again, here we have open issues. So there's an issue tracker, kind of a bug tracker, and we see 381 open issues. So we see lots of people using it, reporting bugs. We see that all of them have got a bunch of replies already. So it's an active community. And this is really what ensures that this project will continue to live and be useful. So to summarize, I went through some best practices for reliable, maintainable software. So open source development with version control, writing tests, writing documentation, having continuous integration to ensure that these tests are always passing, and finally, building a community and enabling people to be involved in a variety of ways. And so if you found that interesting and you want to learn more or maybe put these things into practice, a good way to start is from a template repository. And so on the right here, we have 3 different project templates that we offer from our GitHub page. And you can go there, just click on use this template and it'll generate a new GitHub project for you, which has all of these best practices set up and ready to go. And with a kind of minimal investment, you can then get a lot of benefits from applying these ideas. And so feel free to ask any questions to Roberto or to me. And thank you for your time.
Thanks a lot, Liam, for doing this. So maybe I had an idea before, while we wait for people to ask questions if they want or not. I'm launching a little poll to see where we are with software here in this meeting. Let's see. So you should have a poll that appears on your side. You should be able to click on it. And maybe, Liam, you can stop sharing if...
Yes.
Okay, we have already 27 answers out of 56. Let's see where we go. 33. I'm moving forward slowly, but the answer, I will not spoil anything, but the answers are kind of interesting. We see at the end. And maybe we have 21 people shy that do not want to answer the poll. So maybe I can show you what I see. Let me see. So globally, what I see is that almost everybody is using software tools in research. Then,
Roberto, I think we don't see the good screen. We don't see the result of the.
Ah, you don't see the result?
No.
Kind of. Well, anyway, if I cannot share the screen for some technical reason, let me sum up. So the first question is, do you use software tools in research? And so we have basically 83% answering yes. So most of the people are using software. That's good news because actually you got interested in this talk. But then things become much more mixed up when it comes to actually writing software or reusing software by coming from other places. It is more 50-50. Let's say you have people that use software from others, but only half they actually do write or use it. And what I can see is that most of the people that write it are using a version control system. And apparently everybody knows what open source is. Well, that would be a nice test to check what you know about open source, but we will not do it now. And then when it comes to actually where archiving software, which is relevant, the majority of the answer is nowhere. So I didn't know where to archive it, 54%. Then in institutional archive, 34%. Then Zenodo, 20%. Then software heritage, 9%, and AL, 6%. So still way to go on getting the word out about the possibility of archiving software in general. And this was just a part of the poll, which was kind of generic about your knowledge, knowing a little bit more about who is around the table. That's it. So I hope you actually got some interesting element out of the presentation of today, based again on the result of this poll. But then I don't know if we have any question coming in or not. No, so
no, not in the chat. Perhaps I have one question for both of you. In relation with open science, which is the theme of our training series, it seems to me that your two presentations are very complementary for the documentation of the code to its archiving. And can we say that we are in an approach that respects the FAIR principles for the code if it can be open later?
This is a very interesting question, and maybe it will take some time to explain. Just to recall everybody, probably you know it even better than me, but just to recall what FAIR means. So FAIR is findable, accessible, interoperable, reusable. This is a set of principles that was set out in 2016 in an article by Beremont, Wilkinson, and others. And that was the outcome of a workshop that people really that were interested in data in research were trying to understand where were the blockers in reusing data properly, etc. So they came out with this principle that then became a kind of a buzzwords which are used everywhere. But just to provide you my personal point of view, and you are pretty free to disagree. So FAIR principles are very well designed for data. Okay, why? Because they focus a lot on the issue about metadata. So findable, accessible. If you look at what is in the implementation of this principle, there is a lot of stress on the importance of putting proper metadata with common vocabularies among the disciplines, etc. Of course, this is super important. I do not know where you work, but for example, if you're in a field where a friend of yours, a colleague of yours ships to you a gigantic file with tens of thousands of lines of comma-separated values, and you have not the slightest idea what is in column 1, 2, 3, 4, or 5, or how the data are represented, what is the format for the date or for the numbers, etc., you cannot do anything with that. Okay, it's a mess. That's not a piece of data you can reuse. It is just a gigantic mess. So stressing a lot the importance of putting proper metadata there to know what it is, or for which instrument produces this data, and making sure you can integrate it in a pipeline for doing late aggregation of data, etc. That's super important. It cannot be stressed enough. But when you move out of data and you come into other things like publication or software, then the issue is not really about putting metadata, right? So when you have an article, all the relevant metadata is already there. You have the authors, you have the keywords, you have the title, you have the journal. So what other metadata do you want? And then when you come to software, it's very similar. I mean, software which is decently written, it already comes with tons of information inside because it is a technical object. If you don't provide it, you cannot reuse it. There is a make file, there is a description, there is a readme, there is a file that tells you how to install it. I mean, there should be, if you are following standard, very, very, very old principle of software engineering. Okay? I mean, 30, 40 years ago, it's not new. It's not rocket science. Okay? What is new is much more people today write this software than 40 years ago. But this doesn't mean you need to invent still another principle. Okay? You just need to go back and learn. So using the term FAIR for software or for article is something that make me itch a bit. Okay, so you see, it's not the key point. The key point about software is, did you choose the right license? Did you use the right tool for developing it? Do you have a test suite, etc., this kind of thing? Do you have a sustainability plan? Do you have proper documentation? Did you set up continuous integration? And I think focusing on just the terminology of FAIR is distracting from the key issue. But it's just my personal opinion. Feel free to disagree if you really want to go out and say that FAIR is the alpha and omega open science. Feel free to do that. Liam, what's your take on this?
Yeah, I would tend to agree with what you said. I mean, I think it's a good thing to aim for, but it doesn't match fully with software in the same way that it does for data.
Okay. Any other question? But yes, to answer in a less, I mean, sorry, because this FAIR just makes me itch a little bit, so I reacted there. But the general comment, yes, we fully agree. The presentation were complementary. They are designed to be complementary because developing research software in a proper way, make it reusable, making citable, available, etc., is a complex undertaking that requires many steps. So how you start developing it properly, making sure other people can come in and understand what is going on, making sure you can check that when you accept a modification, you are not breaking something else by proper continuous integration, tracking things with version control system, everything, the beautiful tools that Diane showed us is super important. And then you have this academic part of the work, which is how do we ensure this is available for the long term, how we ensure it is referenced in a proper way, how we ensure we provide credit and citation, etc. And you see, and then you have the extra layer that, I mean, the institutional layer, I mean, how to provide the proper environment for you in research to actually build sustainable components of research software in how to recognize your effort in developing software. And you see, for example, in this direction, here in France, in last February, we announced the result of the first national prize for open science in research software. So the idea was to ask all teams in France to become candidate to this national prize, which was awarded by the Ministry of Research in February in a very beautiful setting of the Open Science European Conference. And that is a first step in giving recognition to the people that make an effort of developing very important, beautiful components, software library, which are used in research. And if somebody is interested, I will be happy to share the links to the result. You will see there are probably pieces of software that you know of in your discipline that got an award in this ceremony. And I would like and hope to see more of these kind of prizes coming up in other countries or at European level or international level to recognize the work and the time and the hour and the night that we as developers spend in building software for others to reuse.